So, in this module we have learnt about the power series method, and we saw how the power series method we took an example of the Legendre equation, and we saw how the power series method could be used to solve the Legendre equation, and we looked at certain special cases when one of the two power series converges, and that gave us Legendre polynomials. And so these Legendre polynomials are also solutions of the Legendre differential equation. Okay, and we saw some properties of these Legendre polynomials. Now, where do Legendre polynomials appear in various physical theories? So we said that whenever we are dealing with a spherical system and we are dealing with waves in spherical dimensions, then Legendre polynomials naturally appear. So today I'll show how where Legendre polynomials appear very naturally when you are solving the quantum mechanical problem of a rigid rotor. Okay. And in fact the polynomials that appear are referred to as associated Legendre polynomials or spherical harmonics. So where do they appear? So let me describe the problem that we are that you will be solving. So you consider the angular momentum operator. So the angular momentum operator for a single particle, for one particle. Now this operator in quantum mechanics, so I will write the operator for L square, the squared angular momentum. So this is given by minus h bar square dou square by dou theta square plus cotangent of theta dou by dou theta plus 1 by sine square theta dou square by dou phi square. So this is the operator for the squared angular momentum, and the operator for the z component of the angular momentum is given by minus I h bar dou by dou phi. Okay, so this is the operator, and remember we are using spherical polar coordinates. So in spherical polar coordinates, you can imagine that if these are your axes x, y, z, then if you have a point r which has coordinates x, y, z, then we express the coordinates in terms of r theta phi, where r is this distance, theta is the angle with the z axis, and phi is this angle that the projection of this vector onto the xy plane makes with the x axis. So we are using spherical polar coordinates, and in spherical polar coordinates these are the operators for L square and Lz. Now the problem that we are interested in is we are interested in finding simultaneous what are known in quantum mechanics as eigenfunctions of L square and Lz. Okay, we will denote these functions as y of theta phi. So this is the simultaneous eigenfunction of L square and Lz, and what are the properties of y? So it should satisfy that if you take L square operated on y, you should get some constant. I will call that constant as c times, so c is independent of theta and phi, and then if you take Lz operated on y theta phi, you should get some other constant b times y of theta and phi. So this is what we are looking. We are trying to find a y that satisfies these two conditions. Okay, so you want to find a y that satisfies these two conditions, and these two conditions will give you some differential equations. So before we do that, we need now this is a function of two variables. Okay, so we'll use separation of variables so you say y of theta phi is written as a function s which is only a function of theta times t which is only a function of phi. So, we start with this, and if you take this y of theta phi equal to s of theta into t of phi and you substitute in these equations. So, let me emphasize that these two are differential equations. Because L square has a representation that involves derivatives. Similarly, Lz also has a derivative. So, the second case is a first order differential equation, and for L square you have a second order partial differential equation that includes both theta and phi. Okay. Now, if you use separation of variables, okay, then let us say you substitute in the second equation. So, substitute in the second equation. So, what you will get is minus I h bar dou by dou phi of s times t is equal to b times s times t. Okay, I am not showing the theta and phi dependence of s and t. Now, what you can do is you can take since this derivative operates only on the phi part. So, I can write this as minus I h bar s dt by d phi equal to s times bt. Okay, I am deliberately writing the s in front, and what you can do is you can cancel the s, you can just cancel the s on both sides, and this gives you the relation minus I h bar dt by d phi equal to bt. Okay. So, this is the differential equation for t, and it is a really simple differential equation. Okay. So, notice that by separation of variables you went from a partial differential equation. Okay. So, this was a because Lz and L square involve partial derivatives. So, Lz has a partial, it is a partial differential equation for y, and from that you went to an ordinary differential equation for t. Okay. Now, when you do this, okay, so you can solve this, you can show that t is equal to or t is proportional to, I will say it is proportional to e to the I h bar phi. T is actually proportional to I h bar or sorry I b phi. So, just write it correctly. So, it is equal to, so what you will have is if you take the exponential, okay, so you have b divided by I h cross. So, that is I b divided by h bar. So, t is proportional to this. So, I can write t as a constant times e to the I b h by h cross phi. So, let me call that constant a e to the I b by h bar phi. So, this is the solution of the phi part, okay, and just for you can use t of phi equal to t of phi plus 2 pi. Okay, this is because your angle phi varies from 0 to 2 pi, and if you rotate by, if you increase your angle by 2 pi, then you get back to the original angle. So, this implies a is equal to 1 by root 2 pi. Okay, and this you can show using normalization. Oh, sorry, before I do that, okay, so we will come back to a just a minute. So, if you use this, then what you will get is that e to the I b phi by h bar is equal to e to the I b by h bar phi plus 2 pi. Okay. And if you cancel the e to the I b phi by h bar, you get e to the I b by h bar into 2 pi is equal to 1. Okay. And you know that so if b by h bar was an integer, then e to the 2 pi I into any integer is 1. Okay. So this implies that b by h bar equal to m integer. Okay, m has to be an integer. So this says that or b equal to m h bar, this is commonly referred to as a quantization of the z component of angular momentum. Okay. So m is an integer. M is an integer means it can be 0, plus minus 1, plus minus 2, plus minus 3, and so on. Okay. So this is a part of the t. Now if you take this t and you substitute in the L square expression. So you take the form of t, okay, and you substitute in the expression for L square operator, okay, then what you will get is okay. So that is what we are going to do. Before I do that, I will just say that that A can be calculated using normalization condition. So the normalization condition is integral 0 to 2 pi psi star psi, or rather t star t, t star t d phi equal to 1. Okay, this implies, you can easily show that A is equal to 1 by square root of 2 pi, because the complex conjugate of t is just this multiplied by the minus sign. So it is just e to the minus I b by h cross phi. Okay, and so I can write, with this I can write t is equal to 1 by root 2 pi e to the I m h phi, e to the I m phi. Okay, so this is my expression for t, and now I can take this expression for t and substitute in the expression, in the equation for L square. So the equation for L square is this. So L square has this long expression, and L square y is equal to cy. So we are going to use that, we are going to substitute y equal to, so I can write y of theta phi is equal to s of theta times 1 by root 2 pi e to the I m phi. Okay, when I substitute this form of y into the expression, into the eigenvalue equation for L square, what I will get is the following. So what I will get, I will just write it explicitly, minus h bar square, and you have dou square by dou theta square plus cotangent of theta dou by dou theta plus 1 by sine square theta dou square by dou phi square, and what you have, y, instead of y I will write s of theta, which is only a function of theta, and then you have 1 by root 2 pi e to the I m phi. Okay, and this is equal to a constant c times y itself, and y is s of theta times 1 by root 2 pi e to the I m phi. Okay, so this is our equation. This is the differential equation, and now we'll take this inside. Okay, when you take this inside, this is the third term is the only one that has derivative with respect to phi. Okay, so the first two terms do not have derivatives with respect to phi, and when you take the second derivative with respect to phi, you will just get minus m square times the same function. So what I will get is, I can write this as minus h bar square, and I will have e to the I m phi, okay, and divided by root 2 pi. Okay. And then what I will have is, I will have d square s by d theta square plus cotangent of theta ds by d theta plus rather it will become minus m square s by sine square theta. Okay, so I have m square minus m square times e to the I m phi. E to the I m phi I took outside, so this is what I am left with, and this is equal to c s e to the I m phi by root 2 pi. Okay, so I can just cancel the e to the I m phi on both sides, and what I am left with is a differential equation that involves only s. okay, and let me write down the differential equation. I will take the h square to that side. So, what I will have is d square s by d theta square plus cotangent of theta ds by d theta minus m square s divided by sine square theta is equal to c by h bar square into s with a minus sign, minus c by h bar square. Okay. Okay. So this is a differential equation that we have to solve for s. Okay. And what we will do is we will make a few changes. We will make a change of variables. Okay. We'll change the variable because we see the sine square theta appearing here and you see a cotangent theta appearing here. Okay. Now we want to write it, we want to get an algebraic, we want an equation without all these sines and cosines. So we change the variable, you put w equal to cosine theta. So when you put w equal to cosine theta, then instead of your function s of theta, you have a function g of w. Okay, I am just using a different symbol g. Okay, you can also write it as s of w, but I will use a different symbol g of w. Okay, because s of theta is basically equal to g of w. Okay, so then what you can do, then if you take any derivative, ds by d theta is ds by d or so I can write ds by d theta is equal to dg by dw into dw by d theta, and I can do dw by d theta as just minus sine theta. So I can use this iteratively. I can so this is just minus sine theta dg by dw. Okay, and I just go ahead and I make all these substitutions and put in this equation. Okay, so the minus sine square theta, we will find that it eventually cancels this factor. So what you will get is a differential equation that looks in the following form. So I will just write the final equation. Okay, you can easily work it out. So you will get 1 minus w square. Okay, so the sine square theta is gives you a 1 minus cos square theta. Okay, so and that is 1 minus w square, and what you will get is d square g by dw square, okay, minus 2w dg by dw, okay, plus c by h bar square times minus m divided by 1 minus w square g equal to 0. Okay, and you can see what has happened. This almost looks like a Legendre differential equation. Okay, not exactly like one, but it almost looks like one. Okay. Also notice that the range of allowed values of w, okay, w is cos theta, and theta varies from, theta goes from 0 to pi. So this implies w equal to cos theta, that varies from minus 1 to 1. Okay, so the range of w is minus 1 to 1. Okay. Now what we will do is we don't want this additional m term there. Okay. So what we will do is we'll do a small change in this. Okay, because we have a 1 over 1 minus w square in the denominator, which we would not like to have. Okay. So it looks a lot like the Legendre differential equation if you look at this. Okay, but there is a 1 minus w square here. Okay, so to get rid of that, we will make a substitution. So you use g of w is equal to 1 minus w square raised to m by 2 h of w. Okay, so I'm again defining this new function h in this form. So I'm writing g as this. Okay, and it will become obvious why we are doing this. Okay, so when you do this, then the differential equation, you do this and you substitute everywhere, you substitute in each of these terms. Okay, then you can write the differential equation in the following form: 1 minus w square. Okay, now I will just call it I won't write a second derivative, I will just write it as h double prime, which is second derivative with respect to w. Okay, minus 2, and what I have is absolute value of m plus 1 W H prime plus what I will have C H bar square minus absolute value of m plus 1 H equal to 0. Okay. Now, this equation, okay, is I mean with whatever constant you have in this last term, this is of the form of what is called an associated Legendre equation. Okay. And this is what is used to I mean we use the properties of this equation. Okay. Now you can work out the solution of this using the power series method. Okay. And that is what we are going to do. Okay. But I will just do a few steps. Okay. And then we will look at the implications of the results. So what we are going to do is we are going to write this in the form of a power series. So the power series, so what you are going to say is that H of W, okay, you are going to write it as sum over j equal to 0 to infinity, and what I will write is as a j W of j. Okay, I will just write it as a j W of j. Okay, and I've used the letter j, okay, and this is what you do in the power series method. Now if you substitute in this, okay, you will get the recursion relation that looks like aj plus 2, okay, is equal to j plus absolute value of m, okay, j plus absolute value of m plus 1 minus c divided by h bar square. Oh, this should be c divided by h bar square. So divided by h bar square. This should have been c divided by h bar square in the differential equation. Okay. So this, the whole thing divided by j plus 1, j plus 2 times a j. Okay. And you can see from here that it looks a lot like the recursion relation for the Legendre polynomials. In fact, these polynomials are called the associated Legendre polynomials, which are closely related to the Legendre polynomials. Okay. Now what we said is that if this series has to terminate, okay, so if series has to terminate at j equal to L, okay, then we must have this numerator when j equal to L should go to 0. So, you should have L plus m, L plus mod m plus 1 minus c by h bar square equal to 0. Okay. Or you will get the relation which is you will get c is equal to h bar square L plus m, L plus mod m plus 1. Okay. And L is an integer. Okay. M already we showed to be an integer. Okay. So, L plus mod m is another integer, we will call it k. Okay, we will call it k. So, this is h bar square k plus 1. So, k is equal to L plus mod m. This is an integer, this is a positive integer equal to integer, and you know, when you wrote the series, L can be anything from 0, 1, 2, 3, etc. So, this is equal to 0, 1, 2, etc. So, absolute value of m has to be 0, 1, 2, etc. So, L plus m will go from 0, 1, 2, etc. Okay. So we got that. So this is the eigenvalue of L square. So, what you can say is that L square y is equal to h cross square k k plus 1, where k is some integer y. Okay. This is a very well known result that we use. We use this to characterize the states of a rigid rotor in quantum mechanics. Okay. And so we saw how we can get this by using the power series method. Okay. A few more points I want to make, okay, just to complete. So when this series terminates, okay, then the solutions, okay, so this y of theta phi takes the following form. Okay. So I can write it as 1 by root 2 pi e to the I m phi, okay, times what I have is something that is s. Now s is a function of theta and phi, but it depends on these two quantum numbers. What I would like to use the notation, so change notations. So I would just like to make a small change of notation. Let me call this place where the series terminates as k. Okay, so I'll just make this change of notation. So where the series terminates, I'll call it k, and I'll use L to denote, and I'll use L to denote the value of k plus L. So I'll call this k, and I'll use the notation L, just to be consistent with what you're used to seeing in various books. So use the notation L plus 1, where you have L equal to k plus m. Okay, just to be consistent with the notations that you are used to seeing. So I said the series has to terminate at j equal to k, then you must have this relation. Okay, now this L, now your y has this form, so you have e to the I m phi. Now this s depends not only on, it depends on L and it depends on m. Okay, s L m of theta. Okay, so this is the function of theta. Now what is this function of theta? This will be related to the solution. This will be related to the polynomial that you get from the power series solution. Okay, so that polynomial, so you can show that s L m of theta. Okay, so this is proportional to, okay, we won't bother about the constant of proportionality. Okay, so P L, the notation is P L m of, now the variable, so you remember what we had was a w was cos theta. Okay, so the variable in which we wrote the associated Legendre equation was w, which is cos theta. Okay, so this polynomial is called the associated Legendre polynomial. Okay, it is closely related to the Legendre polynomial. So Legendre polynomial, you just had PL. Okay, now you have PL and M. Okay, so what is the expression? I'll just write the expression. So if I write PL M of W, okay, so I can write this as, so there are some constants at the beginning, just like in the Legendre polynomial. Then you have 1 minus W square raised to absolute value of M by 2. Okay, and then you have exactly like the Legendre polynomial, but instead of just L, you have L plus M. Of W square minus 1. So instead of 1 minus W square, you have W square minus 1 raised to L. So this is the associated Legendre polynomial, which appears naturally in solution of the rigid rotor problem in quantum mechanics. Okay, and with this I will stop today's lecture. Okay, so in the next class we will look at another differential equation called the Hermite equation. Okay, and we will look at Hermite polynomials which appear in that solution. Okay, thank you.